In group theory, a branch of mathematics, the term order is used in two unrelated senses. The order of a group is its cardinality, i.e., the number of elements in its set. Also, the order, sometimes period, of an element or of a group is the smallest positive integer m such that m equals e. If no such m exists, A is said to have infinite order, the ordering relation of a partially or totally ordered group. This article is about the first notions. The order of a group G is denoted by order G, and the order of an element A is denoted by order A. Example. The symmetric group S3 has the following multiplication table. This group has 6 elements, so order equals 6. By definition, the order of the identity E is 1. Each of S, T, and W squares to E, so these group elements have order 2. Completing the enumeration, both U and V have order 3, for U2 equals V and U3 equals V equals E, and V2 equals U and V3 equals UV equals E. Order and structure. The order of a group and that of an element tend to speak about the structure of the group. Roughly speaking, the more complicated the factorization of the order, the more complicated the group. If the order of group G is 1, then the group is called a trivial group. Given an element A, order equals 1 if and only if A is the identity. If every element in G is the same as its inverse, then order equals 2 and consequently G is abelian, since by elementary group theory, the converse of this statement is not true. For example, the cyclic group Z6 of integers modulo 6 is abelian, but the number 2 has order 3. The relationship between the two concepts of order is the following. If we write for the subgroup generated by A, then for any integer k, we have AC equals E if and only if order divides k. In general, the order of any subgroup of G divides the order of G. More precisely, if H is a subgroup of G, then order equals G. H, where G, H, is called the index of H in G, an integer. This is Lagrange's theorem. Equals infinity. The quotient or does not make sense, as an immediate consequence of the above. We see that the order of every element of a group divides the order of the group. For example, in the symmetric group shown above, where order equals 6, the orders of the elements are 1, 2, or 3. The following partial converse is true for finite groups. If D divides the order of a group G and D is a prime number, then there exists an element of order D in G. The statement does not hold for composite orders, e.g., the Klein 4 group does not have an element of order 4. This can be shown by inductive proof. The consequences of the theorem include: the order of a group G is a power of a prime P if and only if order is some power of P for every A in G. If A has infinite order, then all powers of A have infinite order as well. If A has finite order, we have the following formula for the order of the powers of A. Order equals GCD, K, for every integer K. In particular, A and its inverse A-1 have the same order. In any group, there is no general formula relating the order of a product AB to the orders of A and B. In fact, it is possible that both A and B have finite order while AB has infinite order, or that both A and B have infinite order while AB has finite order. An example of the former is A equals 2x, B equals 1x with AB equals x1 in the group. An example of the latter is A equals x plus 1, B equals x1 with AB equals id. If AB equals bar, we can at least say that ORD divides LCM, ORD. As a consequence, one can prove that in a finite abelian group, if M denotes the maximum of all the orders of the group's elements, then every element's order divides M, counting by order of elements. Suppose G is a finite group of order n, and D is a divisor of n. The number of order D elements in G is a multiple of phi, where phi is Euler's totient function, giving the number of positive integers no larger than D and coprime to it. For example, in the case of S3, phi equals 2, and we have exactly 2 elements of order 3. The theorem provides no useful information about elements of order 2, because phi equals 1, and is only of limited utility for composite D such as D equals 6. Since phi equals 2, and there are 0 elements of order 6 in S3. In relation to homomorphisms, group homomorphisms tend to reduce the orders of elements. If F, GH is a homomorphism, and A is an element of G of finite order, then ORD divides ORD. If F is injective, then ORD equals ORD. This can often be used to prove that there are no homomorphisms between two concretely given groups. A further consequence is that conjugate elements have the same order. Class equation. An important result about orders is the class equation. It relates the order of a finite group G to the order of its center Z and the sizes of its non-trivial conjugacy classes. Where the die are the sizes of the non-trivial conjugacy classes, these are proper divisors of G, bigger than 1, and they are also equal to the indices of the centralizers in G of the representatives of the non-trivial conjugacy classes. For example, the center of S3 is just the trivial group with the single element T, and the equation reads, S3 equals 1 plus 2 plus 3. Open questions. Several deep questions about the orders of groups and their elements are contained in the various Burnside problems. Some of these questions are still open.